The video topic is Digital Twins: Concept, Origin, Technologies, Algorithms, Programming, AI, and Quantum Computing Foundations and Applications in Complex Engineering Systems. Digital twins represent one of the most transformative paradigms in modern engineering and computational science. At their core, digital twins are living virtual representations of physical systems that are continuously synchronized with real-world data. Unlike static simulations or offline models, digital twins evolve over time, learning from data, adapting to environmental changes, and supporting real-time decision-making. Their emergence reflects a fundamental shift in engineering practice, from reactive and descriptive analysis toward predictive, prescriptive, and autonomous systems. In an era characterized by complexity, uncertainty, and scale, digital twins provide a powerful framework for understanding, managing, and optimizing complex engineering systems. Historical origin and evolution of the digital twin concept. The conceptual roots of digital twins lie in systems engineering, control theory, and product lifecycle management, (PLM). Early engineering models were largely static and used primarily during the design phase, with little or no connection to operational data. The modern digital twin concept gained prominence in the early 2000s, particularly through aerospace and defense applications led by NASA, where high-fidelity virtual replicas of spacecraft were employed to simulate faults, predict failures, and support mission-critical decisions. As sensing technologies, computing infrastructure, and connectivity matured, these early simulations evolved into continuously updated, data-driven twins, marking the transition from offline modeling to real-time cyber-physical integration. Formal definitions and core concepts. A digital twin can be defined as a dynamic, executable digital representation of a physical system that is continuously updated using real-time data and capable of prediction, optimization, and decision support. It is important to distinguish between a digital model, which is static and disconnected from live data, a digital shadow, which receives one-way data from the physical system, and a true digital twin, which maintains bidirectional data and control flows. This bidirectional coupling enables learning, feedback control, and adaptive optimization throughout the entire system lifecycle. Digital twin architecture and system frameworks. A digital twin typically follows a layered architecture. The physical layer consists of real-world assets, processes, or environments. The data acquisition layer captures measurements via sensors, IoT devices, and embedded systems. The communication layer ensures reliable, secure data transfer. The virtual layer hosts physics-based, data-driven, or hybrid computational models. Above this sits the intelligence layer, where analytics, optimization, and AI-driven reasoning occur. Finally, the control and feedback layer allows the digital twin to influence physical system behavior through recommendations or automated actuation, closing the cyber-physical loop. Enabling technologies for digital twins. Digital twins are made possible by the convergence of several advanced technologies. IoT and embedded sensing enable continuous observability of system states. Edge, cloud, and high-performance computing (HPC) platforms provide scalable computational resources. Cyber-physical systems (CPS) frameworks integrate computation with physical processes in real time. Data integration and interoperability technologies, including APIs and middleware, enable heterogeneous systems to operate as a coherent digital ecosystem. Together, these technologies transform digital twins from conceptual models into operational engineering platforms. Mathematical foundations of digital twins. At a fundamental level, digital twins are grounded in mathematical modeling of dynamic systems. State space formulations describe system evolution, often governed by ordinary or partial differential equations. Real-world uncertainty necessitates stochastic modeling and probabilistic inference, while optimization theory supports decision-making under constraints and competing objectives. Control theory provides the mathematical foundation for stability, robustness, and performance regulation. These mathematical principles ensure that digital twins remain scientifically rigorous and computationally reliable. Algorithms used in digital twin systems. Digital twin implementations rely on a diverse range of algorithms. Numerical simulation algorithms solve physics-based models. State estimation methods, such as Kalman and particle filters, reconcile noisy sensor data with model predictions. Optimization algorithms, including multi-objective and constrained approaches, enable operational tuning and design exploration. Real-time decision-making and scheduling algorithms ensure responsiveness in time-critical systems. Collectively, these algorithms form the computational core of digital twin intelligence. Artificial intelligence in digital twins. Artificial intelligence significantly enhances the power of digital twins. Machine learning enables data-driven model discovery when first principles knowledge is incomplete. Deep learning supports perception, anomaly detection, and pattern recognition in high-dimensional sensor data. Reinforcement learning enables adaptive control by allowing digital twins to learn optimal strategies through interaction with their environment. Through AI, digital twins evolve from passive mirrors into adaptive, predictive, and self-improving systems. Agentic AI and autonomous digital twins. A key emerging direction is the integration of agentic AI, where digital twins function as autonomous agents capable of sensing, reasoning, decision-making, and action. In complex environments, multiple digital twins may interact as multi-agent systems, cooperating or competing to optimize system-level objectives. This paradigm supports decentralized decision-making, scalability, and resilience, enabling digital twins to manage complexity in distributed engineering systems. Computer programming and software engineering for digital twins. The development of digital twins requires advanced computer programming and software engineering practices. Model-based systems engineering, MBSE, ensures consistency across design, simulation, and operation. Event-driven and agent-based programming paradigms support asynchronous data flows and real-time interaction. Digital twin platforms must integrate legacy systems, real-time data pipelines, and AI components, demanding modular, reliable, and maintainable software architectures. Programming languages, platforms, and tools. Digital twins are commonly implemented using Python, C, C++, Java, and MATLAB, supported by numerical libraries, physics solvers, and simulation engines. Cloud-native platforms enable elastic scaling, while edge computing frameworks support low-latency control and autonomy. DevOps and MLOps practices are increasingly critical for continuous deployment, model updating, and lifecycle management of digital twin systems. Data management and digital twin intelligence. Data is the lifeblood of digital twins. Real-time data streaming architectures, sensor fusion techniques, and distributed databases are required to manage high-volume, high-velocity data. Ensuring data quality, provenance, cybersecurity, and privacy is essential, particularly in safety-critical and regulated domains. Robust data governance frameworks underpin the trustworthiness and effectiveness of digital twin intelligence. Quantum computing and digital twins. As digital twins scale in complexity, classical computing approaches face limitations in optimization, simulation, and combinatorial decision-making. Quantum computing offers new possibilities by enabling faster exploration of large solution spaces and more efficient simulation of complex physical systems. Hybrid classical quantum architectures are emerging as a promising pathway for next-generation digital twins. Quantum AI and quantum-enhanced digital twins. The convergence of quantum computing and artificial intelligence introduces the concept of quantum-enhanced digital twins. Quantum machine learning, quantum optimization, and quantum game theory have the potential to accelerate learning, improve coordination among multiple digital twins, and enable superior decision-making in highly complex environments. Although still an emerging field, quantum AI represents a strategic frontier for digital twins in advanced engineering systems. Validation, verification, and trustworthiness of digital twins. A critical requirement for operational digital twins is trustworthiness. Validation ensures that the digital twin accurately represents the physical system, while verification confirms that the computational models and software are implemented correctly. As systems evolve over time, model drift can occur due to component aging, environmental changes, or operational variability. Continuous validation using live data, explainable AI methods, uncertainty quantification, and confidence bounds is therefore essential. Trustworthy digital twins must also address transparency, auditability, and regulatory compliance, especially in safety-critical domains. Digital twins in complex engineering systems. Complex engineering systems are characterized by nonlinearity, high dimensionality, strong coupling, uncertainty, and emergent behavior. Digital twins provide a unifying framework for managing such complexity by integrating physics-based models, data-driven learning, and real-time feedback. Rather than simplifying complexity away, digital twins allow engineers to embrace complexity, explore scenarios, and understand system behavior under extreme or unexpected conditions. This capability is particularly valuable in large-scale infrastructure, energy networks, and interconnected socio-technical systems. Applications in manufacturing and Industry 4.0. In manufacturing, digital twins are a cornerstone of Industry 4.0. They enable virtual commissioning of production lines, predictive maintenance of equipment, real-time quality control, and dynamic production optimization. By simulating process variations and equipment degradation, manufacturers can reduce downtime, improve yield, and increase operational flexibility. Digital twins also support mass customization by enabling rapid reconfiguration of production systems in response to changing demand. Applications in robotics and autonomous systems. Digital twins play a central role in robotics by supporting design, simulation, training, and real-time operation. They enable sim-to-real transfer, allowing robots to be trained extensively in virtual environments before deployment. During operation, digital twins monitor robot health, predict failures, and optimize motion planning and control strategies. In multi-robot systems, digital twins facilitate coordination, task allocation, and collision avoidance. They are particularly critical in autonomous robots operating in uncertain or hazardous environments. Applications in energy and power systems. In energy systems, digital twins support the management of increasingly complex and decentralized networks. Applications include smart grids, renewable energy integration, power asset management, and demand-side optimization. Digital twins enable real-time balancing of supply and demand, predictive maintenance of critical infrastructure, and resilience analysis under extreme weather events. As energy systems transition toward sustainability, digital twins provide essential decision intelligence for reliability and efficiency. Applications in water resources and environmental systems. Water systems are inherently complex, influenced by climate variability, human behavior, and infrastructure constraints. Digital twins are used to model water quality, treatment processes, distribution networks, and catchment dynamics. They support real-time monitoring, predictive contamination detection, and optimization of treatment strategies. In environmental management, digital twins enable scenario analysis for flood mitigation, drought planning, and climate adaptation, supporting evidence-based policy and operational decisions. Applications in buildings and smart cities. Digital twins of buildings and urban environments enable intelligent infrastructure management and sustainable urban planning. They integrate structural models, energy systems, occupancy patterns, and environmental data to optimize performance and comfort. In smart cities, digital twins support traffic management, mobility planning, energy efficiency, and disaster preparedness. By enabling holistic, data-driven urban management, digital twins contribute to more resilient and livable cities. Applications in healthcare and biomedical engineering. In healthcare, digital twins are emerging as powerful tools for personalized medicine and medical device optimization. Patient-specific digital twins can model physiological processes, disease progression, and treatment responses. In biomedical engineering, digital twins support the design and optimization of implants, prosthetics, and rehabilitation devices. They also enable virtual clinical trials, reducing cost and accelerating innovation while improving patient safety. Applications in fire, disaster, and risk management. Digital twins are increasingly applied in fire engineering, disaster response, and risk management. By integrating computational fluid dynamics, sensor data, and predictive analytics, digital twins can simulate fire dynamics, smoke propagation, and evacuation scenarios in real time. In disaster management, digital twins support early warning systems, resource allocation, and emergency response planning. These capabilities are critical for reducing loss of life, property damage, and environmental impact. Economic, business, and strategic impacts. Beyond technical benefits, digital twins deliver significant economic and strategic value. They reduce operational costs through predictive maintenance, improve asset utilization, and enable new data-driven business models such as digital twin as a service. For executives and policymakers, digital twins provide decision intelligence that supports long-term planning, risk management, and investment prioritization. At a national level, digital twin adoption enhances productivity, competitiveness, and technological sovereignty. Challenges and opportunities. Despite their promise, digital twins face several challenges. These include high development and computational costs, data availability and quality issues, cybersecurity risks, and integration with legacy systems. Organizational barriers, such as skills shortages and resistance to change, can also hinder adoption. Addressing these challenges requires interdisciplinary expertise, robust governance frameworks, and sustained investment in capability development. Future trends and research directions. The future of digital twins lies in greater autonomy, scalability, and intelligence. Emerging trends include self-evolving digital twins that continuously learn and adapt, large-scale digital twin ecosystems spanning entire industries or regions, and tighter integration with AI agents and quantum computing. Research is increasingly focused on explainability, trust, and ethical deployment, ensuring that digital twins remain reliable and socially responsible technologies. Policy, standards, and governance. As digital twins become mission-critical, the need for clear standards and governance frameworks grows. Policies must address data ownership, privacy, cybersecurity, and accountability. Interoperability standards are essential for integrating digital twins across organizations and sectors. Ethical considerations, including transparency and fairness, must be embedded into digital twin design and deployment to ensure responsible innovation. Conclusion: digital twins have evolved from simple simulation models into foundational technologies for intelligent, autonomous, and resilient engineering systems. By integrating advanced mathematics, algorithms, software engineering, artificial intelligence, and quantum computing, digital twins provide unprecedented capabilities for understanding and managing complexity. As adoption accelerates across industries and domains, digital twins will play a central role in shaping the future of engineering, infrastructure, healthcare, and sustainability, enabling smarter decisions, safer systems, and a more resilient world. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.